So our second talk is about machine learning tools for rapid control, calibration, and characterization of QPUs and other devices. And Shai is going to tell us about his awesome qoptimize.org platform. Thank you very much. And please go ahead and share your screen.
Right, let's get started.
It's looking great.
Can you guys see?
Mm-hmm.
Okay, good. All right, so I'm gonna tell you about the work we've been doing basically over the past couple of years. These are the people that actually did the work. The group is of Frank Wilhelm Mauck, and we had the graduate students, Nicholas, Federico, Kevin, Anurag, which at the time was a volunteer. Everything I'm going to talk about, all the software is available at qoptimize.org. You'll have this written basically on every slide, and these are the guys that paid for this work. So, the slides are auto-moving. I'll need to figure out why. Okay, never mind. Oh. All right. Okay, a bit of terminology, so we're on the same page. Optimal control is what I call when we have a model and we do an open loop optimization based on some simulator trying to achieve a certain operation, let's say a gate. Calibration is model free, and it's a closed loop operation where you're modifying essentially the control shapes, right? The pulse shapes, lasers, microwaves, whatever they are. And characterization is determining the model of the actual device. Now, we define a good model, and it can also known maybe as a digital twin in some sectors, is a model that predicts the behavior of the system for the operations we wish to perform and for the accuracies we care about. So the last two lines are really important because you can say that you have a good model of a system because you know everything that, for example, for all the signals you can generate with your waveform generator and for, let's say, 0.9999, like 4 or 5 nines. So it's an achievable goal to get a good model. And if you have a good model, then from it you can derive using optimal control the best possible gates. You can do error budget. You can do all kinds of stuff. Okay. Next. I think that a lot of the time we've been doing things a little bit wrong. The standard procedure is kind of known as ad hoc. We design a device, we fabricate it, we do some characterization, not too much usually. Then maybe we use optimal control to derive the pulse shape. Then we measure the fidelity. We realize things don't really work so well, so we adjust the pulse shape. We measure the fidelity and repeat this calibration closed loop process. The thing is that if we needed to do pulse calibration, we essentially proved that the model was wrong, that the model we use in optimal control is wrong. And at the end of this process, we have working pulses, but we don't quite understand why, because we haven't learned anything about the system. We just found pulses that work. And, you know, we need a good model because from a good model, you can determine an error budget, meaning what are the limits of the device that are causing the imperfections you're seeing in the gates. And without an error budget, you can't know what to fix in the next iteration of the design of the device. So a good model is extremely important. Now, getting good gates are really, really hard. They're actually the current limiting factor for quantum computing performance. Like an example, IBM best quantum volume is 64, which means they're doing 36 entangling gates before the fidelity drops below 2/3. And clearly you can't do anything useful with 36 entangling gates on 64 qubits. And the quantum supremacy experiment from Google, right? 99.8% of the data was noise. And they needed 30 million shots to get a statistically significant observation. And if I look at the gate fidelities, Then in Martinez 2014 paper, he had 994, and essentially the same fidelities 5 years later in the supremacy paper. So yes, this is the hero gate, and this is kind of the typical fidelity on a large chip, but still we haven't made huge progress there. And the way we do calibration is really not good enough. This is the calibration graph from Google. This is kind of very specific, very tailored to the individual system. It requires huge resources to set up. And at the end of this whole process, you don't really understand things a lot better. You just have something that works. And characterization is similarly hard. And we need to do better. So we tried to think of how to do better. And this is what we came up with. We call it C3. It's a combination of 3 learning steps or 3 optimizations, however you wish to call it. The first is optimal control, right? We take a model or several models or PDF over the space of models. We do optimal control, and we get a set of pulses or set of gates that perform certain operations. Step number 2 is calibration. We kind of put the models aside, and this is really important because our models may be wrong. They may, for example, neglect a certain phenomena that doesn't appear in the model. So you need to, at some step, go beyond the model you think you know. So we do this calibration, and then the final step is the model learning. We take all the data that we saw in the experiment during the calibration, and we try to fit the model to the data. The result is a better model or set of models, and this whole process can repeat. Now, the way we implemented this is by basically defining the propagation and the goal function and everything as a TensorFlow computational graph. That allows us, of course, to do automatic differentiation, and then the C1, which is the optimal control, and C3, which is the model learning, can then do gradient-based optimization based on this. Okay. Now, the example I'm going to give is on a synthetic device, meaning we kind of simulate the device we're trying to learn so that we have full control over everything. The device includes 2 transpond qubits, several levels for each. We have the coupling, we have shot noise, we have initial thermal state, we have relaxation, readout confusion matrix, we have dephasing. It's quite a rich model. Now, of course, if you go to a typical experiment, this is, for example, at IBM Zurich, it's not clear exactly where the C of t in the Hamiltonian comes in, right? Where's the prefactor of the control Hamiltonian comes in. So what we needed to simulate in addition is the whole chain of control processing, meaning you start with this arbitrary control shape, you go through the discretization that goes with an arbitrary waveform generator, you put a response function on top of that, there may be crosstalk between the control lines, then you have the time evolution, from that you derive populations, and then the readout, but the readout can, of course, have a confusion matrix because nothing's perfect. So we actually have quite a rich model, and we're now working on non-Markovian. That should come up quite soon. So kind of having this rather rich simulator, and for some reason I have the same thing twice, so let's ignore it. And what we'll do is we'll walk through an attempt to understand the system through 3 layers of models. The simplest model is very naive, 2 uncoupled qubits. The second model will couple the qubits, but leave out everything else. And then we have the full model that contains kind of all of the elements. Okay, so first we do the very simple thing. We take the model, based on the model, we do some open loop optimal control, and we get a gate, right? This is the inline and quadrature components of the controls. Okay, that's kind of pretty standard. And now we do a full simulation of the calibration process. Okay? This is a single length randomized benchmarking, and you kind of every point we take are these small blue dots. Okay? The important thing here to notice is first, yes, the fidelity is improved. We're modifying the pulse shape. We forget about the model. And we accumulate a lot of data, quite a big data set. And this data set is about to go into model learning. Okay? Now, in the model learning, what we're trying to do, we're measuring the statistical distance between the simulated results and the experimental results. Okay? Now, of course, this is an experiment, so there's noise. And we have no expectations that the match will be perfect at any point. But we can start doing this learning process for the simple model. And we see that the best we can get is that the distance between the simulation and experiments is about 8 sigma. That's not very good, obviously. And we can see here, again, if we have the experiment and the model, we can see that there's quite a clear mismatch between them. If we then progress to the more accurate or slightly better model where we couple the two qubits, there is some improvement, but it's not much better, and we can't really get lower than around 8 sigma. And when we put in the full model, then you can see that you have a very good match between simulation and experiment, and you go down to essentially 0 sigma, meaning this is as good as can be expected. Right? Now, when we say 0 sigma here, this does not mean that the simulation matches the noise of the experiment, right? That would be impossible. The 0 sigma here means it's as good as can be expected given the noise that we know we have in the system. Okay. All right. So essentially there is some statistical difference here, but we essentially subtract this baseline that we never expect to go better than. And here you can see the improvement process. All right. There's some kind of math here about the Mahalanobis distance we're using to compare kind of the predicted population, etc. I'll kind of skip the top half. One thing that I do wish to point out is that if you look, this is a 2D cut out of the, I don't know, something like 20 parameters we have in the model. This landscape contains quite a few local minima. It is ill-conditioned. This is not a fun optimization to do. But you can do it. You start with an exploration step with something like CMAS. You then continue with the LBFGS once you're kind of in the nice little valley and things progress. Now, one thing we can do here is this is a sensitivity plot. So this is, in this case, the frequency of qubit B. And this is the distance, the y-axis is the distance between the simulation and the experiment in terms of sigma. And you can see that if you have the good model, the full model, then the frequency is rather well localized and it sits on the correct value. Whereas for the simpler models, it's kind of not well behaved and it, you know, in this case, it does sit on the right place, but in the other cases, not so much. Now, I'll skip that and go to this. Okay. Now, it turns out that this whole process of optimal control, calibration, model learning sometimes captures aspects of physics that we kind of forgot about. So what we use for collecting most of the data and doing most of the calibration is single length randomized benchmarking. It's known as orbit. And we also collected the quantum process tomography data. And what we try to kind of constrain and learn is the T1, T2 values, right? The dissipation and dephasing values. As you can see from for example, this line here, you can see that we essentially have no idea what T2 star is. Right? It's essentially flat, so that we cannot distinguish using the data we have between 20 microseconds and 40 microseconds. So we said, okay, let's maybe add a bit of data. We know that experiments like Rabi and Ramsey are typically used to measure T2 stars, so let's use them. We add this data to the data set and re-optimize, but the parameters were still unconstrained. And we could figure out why. So then we started looking at 2D sensitivity plots of T2 star and other model parameters. And what it turns out is that if you have the qubit frequency wrong, this can masquerade as a T2 star value shift. Okay? So in order to make our data insensitive to error in the qubit frequency, you can do a pi flip. You flip the qubit halfway through the experiment. This is known as T2 echo. And once we do that, we get this nice orange line here where T2 star is well localized. Oops, don't know why it went back. When T2 star is well localized and it's more or less correct. So kind of C3 pointed out this T2 echo issue that we kind of forgot as theoreticians. Of course, the experimentalists know all about it, but they live the system every day. Okay, so what additional things can you do with C3? So you can already do an error budget, meaning you can say, okay, let's say my temperature was not 30 microkelvin, but 10 microkelvin. Would the gates be significantly better? Or would it be better if I increase the coupling between the qubits? And once you start asking these sort of questions, then of course the thing that is very natural to think of next is to do co-design, which means that you simultaneously optimize the chip parameters, frequencies and harmonicities, coupling, stuff like that, and the working points for certain, let's say qubits, etc. You can have working points where you kind of preset the qubit, and of course the controls, the gate pulses. And And I think that within like 2 or 3 months, we will have the ability to do co-design. Right? So you will know what's the kind of the optimal way of designing the chip given this certain model or characterization. Now, of course, there's a saying that optimization is a way to remind you which constraints you forgot to put. And for example, if you don't penalize higher anharmonicity with greater noise due to charge sensitivity, what the optimization does is it'll immediately go to extremely high harmonicity. You have a true two-level system, but that's not realistic. So everything has to have a price. So we need quite a robust model that exacts a price for every change in parameters. So that another example is if you have qubits that are tightly coupled, then two qubit gates become very easy, but single qubit gates become very hard because it's almost impossible not to disturb the other qubit. So the measure of performance has to include both 2 qubit gates and single qubit gates. So there's kind of a lot of stuff to take care of, and we're going through this right now. And I think in like 2 or 3 months, it should be ready. Now, given the conference we're at, of course, everything is machine learning. And specifically, optimization can be thought of as a form of reinforcement learning. Now, this is not our work, but this is something we found from the machine learning world, and we're kind of adopting wholeheartedly, which is to think of optimization as a reinforcement learning task. You can see here, for example, a typical situation where you're in a fairly flat valley and a gradient descent keeps bouncing off the walls, right? If the problem is ill-conditioned or something like that. In a reinforcement, why is it keeps advancing on me? I don't know. A reinforcement learning task would kind of identify this behavior and then change the way it chooses the next step to go in a more efficient way. And okay, the thing has a mind of its own. It's moving on its own. Anyway, so the policy in this case, in the context of reinforcement learning, would be something like the hyperparameters. If you have a portfolio optimization, meaning you're using several algorithms and sorry about that, and you're switching between them, then this also is part of the policy, and this can be used, and it should be a lot of fun. Another thing we're working on right now is experiment design, meaning you have a model and you want to design pulses that will measure any parameter or parameters from the model, or distinguish between two competing models for which the current data is unable to tell apart. So one can think of it as essentially a C1 optimal control task. Now, there is a lot of experimental overhead whenever you send a new set of pulses to the experiment. So we really prefer a batched approach where you prepare kind of several pulses to send to the machine, and only then collect the data, as opposed to a very interactive process. And here, essentially, you can think of it as an optimal control task where you want to maximize the information gain, right? As a result of all these tasks with regard to the unknown parameter. Okay, so essentially this is an optimal control task. It happens over multiple pulses and multiple models concurrently, and the goal function has to be changed from the standard Gauss optimization goal function into information maximization. And distinguishing between competing models is actually quite simple. You're looking for a single pulse, where for two models, it'll give very different results, right? So this is, again, just a C1 optimal control task. You could then do stuff like adversarial approaches. So the first thing to do is that we haven't done yet, but we're doing now is switch from L2 to L1 regularization for model learning. Because if you're trying to match experimental data, you're going to have outliers. But then now we're going into more interesting adversarial approaches, right? So you can think of model learning as this adversarial situation where you have a simulator that's trying to essentially fake the experiment, and a discriminator who's trying to tell whether the data is coming from the experiment or from the simulator. And then you kind of train these two together. And you can then take this not only into model learning, but also into calibration, where you think of the gate, you have parameterized gates, and the adversary is trying to find the parameters of the gates, which give you the worst fidelity or the biggest error, while the optimal control is trying to modify the pulses so that it minimizes the error. And that's about it. I think I may be under time, I have no idea. Everything you want you can find here, including the paper, the documentation, the source code, everything. Thank you.
Thank you so much, Shai, for an interesting talk. So we are slowly running out of time, but I think we can squeeze an emergency question.
Ooh, emergency, okay.
Do we have also from the panelists, there is something in Q&A, from Henrik Bloom. In experiments, there are effects such as frequency-dependent crosstalk, transients, transverse functions that are hard to parameterize and learn, but at least in some cases can be dealt with quite effectively via calibration. Is it wise to try to learn all these? Is there a way in the spirit of C3 to avoid that while being able to accurately extract quantities that cannot be calibrated away, such as decoherence channels?
Okay. So I would say this. We believe that getting a very... So you can do quite a lot without learning absolutely everything. Okay, that you can certainly do, but it is really important to, in order to understand what are the limits of the device, to have a really good model, to develop a proper digital twin of the device. And yes, it's a lot of effort, and you don't have to go there if you don't want to. But at least with the C3 approach, we believe you can. I hope that answers the question.
Yeah, I think that was a great perspective. Maybe let's leave it here since we are running out of time. I posted the name of the Slack channel in the chat as well as with the invitation. So I invite you to continue discussion there. And let us move on to the last speaker of this session. Just a note to the organizers. I confirmed with Muhammad that we can keep recording. So let's welcome Muhammad Usman, who is tuning in from University of Melbourne. So exciting times in the morning. And we will switch to yet another third auto-tuning platform, and that will be atomic qubits. Specifically, he will talk about characterization of atomic qubits in silicon via machine learning. Thank you, Muhammad. Welcome. Go ahead.
Thank you very much, and good morning or good evening, depending upon wherever you are. So I'm going to talk about our recent work on characterization of atomic spin qubits in silicon by machine learning. And this work is done with my colleagues, Dr. Charles Hill and Professor Lloyd Hollenberg at University of Melbourne. So just to give you a little bit of introduction of this qubit system. So what we do is we start with the silicon material, which is very famous in microelectronic industry, but we replace some of the silicon atoms selectively by these group 5 elements like phosphorus, arsenic, in some cases antimony or bismuth. So what it does is that if you put, for example, an arsenic atom in silicon, the 4 valence electrons of arsenic will bind with the 4 valence electrons of silicon, but there will be 1 extra electron, 5th electron, which is loosely bound. So we can use either the spin of this extra electron as a qubit, or the nuclear spin of the arsenic impurity atom as a spin qubit. And there are proposals for both electron spin qubits or nuclear spin qubits. You can even construct these 2 spin levels where you can use both electron and nuclear spins as qubits. So this is a very short introduction of the qubit system. How do we experimentally fabricate these devices? Professor Michelle Siemens in our Center of Excellence do the experiments. So she has developed this STM lithography technique where she starts with silicon and she passivates the silicon surface with hydrogen, and by bringing an STM tip, by STM I mean scanning tunneling microscopy tip, which is very popular tool among material scientists. So she can selectively remove some of those hydrogen atoms from the surface, and then she exposed those vacancies to phosphine gas, which plugs in these phosphorus atoms, and then she can regrow the silicon. So you can see, if you are interested, you can see these papers where she has described the lithography technique in more detail. So at the end, what you get is you can place single phosphorus atoms with very high precision. You can make these single atomic thin wires of phosphorus atoms, as you can see in these high resolution images. The question is that, can we make a quantum computer out of this system? Yes, there are several proposals for that. The very first proposal was from Bruce Kane in 1998, Nature paper. And he basically proposed that if you have an array of phosphorus atoms, which are all ionized, you can use the nuclear spins of those phosphorus atoms as qubits, and you can have these gates on top, which are A gates for hyperfine control and J gates for exchange control. And that way you can actually operate these qubits and make large scale quantum information processing. We also, our group also came up with a proposal, which is a 2D architecture compared to this Bruce Kane's architecture. We had top and bottom gates. This paper was published in 2015 in Science Advances, and these red dots, as you can see, they are the phosphorus atoms in silicon. So you can have these top and bottom crisscross gates to control the spins on those phosphorus atoms, and these little squares in between these phosphorus atoms, they are the SET islands, which can selectively load and unload electrons on those phosphorus atoms. So this is one of the proposals to make a large-scale quantum computer architecture out of this qubit system. There are other proposals as well, which have came out afterwards. More recently, we have incorporated exchange interaction, because this 2015 paper that was based on dipole coupling between the phosphorus atom, and those dipole couplings are inherently slow. So now we have incorporated fast exchange interactions, and we can basically operate 2 qubit gates based on the exchange. One of the key issues in these systems is that exchange interaction is very strong function of the positions of those phosphorus atoms or qubits. So as you can see that this is a very old paper by Balita Quayler and her team. And she has shown that if you move those phosphorus atoms, you change as the spacing between them, the exchange varies a lot. And that is potentially a problem, because if you have any small inaccuracy in the placement of the phosphorus atoms, even at the scale of a single lattice site, you will potentially get large variations in exchange, and that will introduce errors in your quantum computation. So the question is that how can we mitigate these sort of errors? There is some work about exchange characterization. You can see this paper from Testerlin, who was in Lloyd's team. They have came up with ideas that you can actually characterize the exchange with very high accuracy, but that comes with an overhead cost, because this characterization takes a lot of time and that slows down your quantum gates. So now the question was that, can we actually locate these qubits or phosphorus atoms after the fabrication in the devices? Because if we can precisely locate these phosphorus atoms in these devices, then we can actually find the exchange interaction with very, very high accuracy. So we started working on this. So this is a brief outline of my talk. So I'll give you a very quick recap of the metrology technique that we have developed to find the exact locations of the phosphorus atoms in silicon. Then I will talk about how we incorporated machine learning to automate the process, and then I'll briefly mention some future consideration. So the way we have developed this metrology technique is again by using this STM tool, which is very popular. It was invented at IBM in 1980s and immediately got Nobel Prize. And it has been used widely in material science community. So these are some of the iconic images taken by this STM tool. And the idea is very simple, that if you have an metallic tip and you have a sample and you apply a bias between them, you can bring those energy levels very close to each other, which allows the electron to tunnel across the barrier. So this is typically operated in vacuum barriers. And then you can measure those tunneling current. And then tunneling current has exponential dependence on either the tip height above the sample or the movement of tip across, because if there are any variation on the surface, the current will exponentially vary. This allows us to take the images of the surfaces with very, very high precision, like literally at atomic scale precision. And in order to model the STM current, Tersoff and Hammond proposed their model in 1985, where they proposed that the STM current is proportional to the mod square of the sample wave function. So that's a very simple model by which you can calculate the current that you measure in STM2. So we started working with over systems. So Professor Sven Rock's team has developed this experiment where they can bring an STM tip and a phosphorus atom is few nanometers below the surface, and they can actually tunnel one single electron through this phosphorus atom to the STM tip. And when they move the STM tip on top of the surface, they get a very beautiful image. So this is an experimental image of the electron wave function, because when you are moving around the STM tip above the sample surface, what you are measuring is that your tunneling current is proportional to the charge density of the electron bound to the phosphorus atom and tunneling through it. So you're actually looking at the charge density plot of a single electron wave function. So they published these experimental images in 2014 Nature Material paper. And then the issue was that when we started to understand these images and we applied this very famous Tersoff theory, we did not match the experiment. The images from theory looked very, very different to the experiment. There was no correlation. And that was a bit of confusion, because in general, Tersoff's theory has been very popular and very successful in estimating STM currents. So we started to look in more detail, and we developed this comprehensive quantum mechanical treatment of this STM current. So in our system, we did this modeling of the donor wave function in silicon over several million atoms. Using tight binding theory, we incorporated vacuum decay of the wave function from the sample to the tip. And then most importantly, we, instead of just looking at the s orbital approximation of the STM tip, which was the basis for tests of theory, we used a more comprehensive tip orbital treatment. So we included all the S, P's, and D's. And then we basically adjusted the weights of those S, P's, and D's to find out which actual, which is the tip orbital which is actually contributing in overtunneling current. So when we did all this modeling and we calculated this theoretical image, and you can see that this matched the experiment extremely well. So we not only captured the symmetry, but the overall size of the features and the brightness of the feature. It was a very good match with the experiment. So that allowed us to understand these measured STM images in a very, very detailed fashion. Going forward, we also observed that if you place these phosphorus atoms in different lattice locations inside the silicon crystal, these images or measured STM currents are very sensitive to the location of the phosphorus atom. So here I'm showing you 4 different locations of the phosphorus atom inside the crystal and the corresponding measured and calculated images. And you can see that each of the image is very different. It exhibits a very distinct symmetry. Even when the 2 phosphorus atoms are at the same depth and they are just one lattice side away in the lateral direction, you can still see very different images, STM images. So this allowed us to map those STM current images back to the phosphorus atom locations. And we can now find the location of each phosphorus atom post-fabrication with very, very high accuracy. Literally, we can find X, Y, Z of the phosphorus atom. And this allowed us to characterize the exchange interaction with very, very high accuracy. So this work was published in Nature Nanotechnology 2016. But the comparison between the experiment and theory was based on pixel by pixel. So there's like every pixel literally was compared from the experiment to theory to create that match. But as you can imagine, that is very slow process. It's a manual comparison. So we wanted to automate it because in general, phosphorus qubits, there could be many phosphorus atoms in a dot. There could not be a single phosphorus atom. There may be different configurations of those dots. So we wanted to have an automated process. And as you can imagine, that machine learning is very useful for image recognition. And this is essentially an image recognition problem. So you measure an STM current, you get an STM image current, and then you just want to recognize that image and map it back to the position of the phosphorus atom for which this image was measured. So recognizing that, we started to look at the machine learning approaches and to be more comprehensive, instead of just having a single phosphorus atom, we also looked at the dots, like 2 phosphorus atoms very close to each other, 3 phosphorus atoms very close to each other, which is a typical condition in experiments. So we developed a scheme to label these phosphorus atom positions in silicon systematically. For example, we put one phosphorus atom at the center, and then we put phosphorus atom as the nearest neighbor configurations or second nearest neighbor configurations, and we label them accordingly. So these are the different images that you can calculate by placing one phosphorus atom at the center and putting as the first nearest neighbor or second nearest neighbor. So you can get all those different STM images computed from the model. And then you can put them in a different depths, and that will allow you to now calculate not only the lateral variations, but also the variations with respect to Z, and you can get a bunch of images from this method. And then based on those images, we trained a convolutional neural network. So we had lots of images. In fact, we have 100,000 images of different donor locations, different noises. I'll explain what sort of noise we put in these images in the next slides. But we computed 100,000 images of STM currents. And then after we trained the convolutional neural network, we tested it on 17,600 images, with different noise levels and different configurations of the phosphorus atoms. And we found that in each case, the convolutional neural network identified not only the exact location of the phosphorus atom, but also the number of phosphorus atoms in the dot. So we were able to fully characterize such systems at large scale. So now digging a bit deeper into the details. So here is the noise. So when we compared our theory images with the experimental images, we observed that there were 2 major types of the noises in experimental data. So one was the asymmetry in the features. So we basically systematically put asymmetric noise. So you can see that this is a very symmetric image without any noise. But if you increase the noise along different axes, you can see that some of the features become very dim. So they almost disappear at very, very high level of noise. So that way we made the images asymmetric, and the axis of that asymmetry was chosen arbitrarily. The second kind of noise which was present in experiment was the blurring of the features. So the ideal theory image is very sharp. All the edges of the features are sharp. They're very clear. But in experiment, often when you measure these images, there are some blurring. Some of the features are more scattered, or the boundaries are not very clear. So we introduce this sort of blurring in our model to be more realistic with the experiments. So we also did some post-processing of the images. We recognize that essentially the information is only in the features. So we filtered the images to highlight the features before training the convolutional neural network. So this is one of the typical image. So we rotated the image. We removed all this black area where there is essentially zero tunneling current. So that highlighted the image section. Then we extracted the edges of the images only, because it's on the information is only in the size of the image or the brightness of the image. So in this particular case, we focused on the size of those features. So we extracted the edges by applying a filter and used these edged images to train the neural network. So in this way, I just wanted to highlight that in this way, we were able to reduce the size of the image from several thousand pixels to only 5,000 pixels. So it's a considerable reduction in the computational space. In the second case, we further reduce the image by focusing only the brightness of the features. So this is again a typical image. So we rotated and removed these zero current areas, but then we place the dimer positions of the silicon surface, because the silicon surface is 2x1 reconstructed. So there are dimers. So we put the dimers, and you can see that each feature corresponds to the dimer, and then we average each feature by a single pixel value. So you can see that each dimer is now, instead of like having a complete continuous feature, it's just a 1 pixel. And that way we were able to drastically reduce the images from several thousand pixels to only 110 pixels. So now each pixel in this reduced image is basically representing the average brightness of one feature in the image. So we use these techniques. So this is the overall idea of the block diagram. So this is over a grayscale image directly possibly measured from experiment or calculated from theory. We convert it to grayscale. So this is the RGB image. We convert it to grayscale. Then we do these two filtering processes, either the edge detection or the averaging of the features. Then we train two separate convolutional neural networks based on these two types of the images or the filtering processes that we have done. So we had this input layer, hidden layer, output layer, the standard convolutional neural network structure. And then we did when we trained it and we tested it, we were able to find that during the training, the learning accuracy was above 99.9%. So it learned those image features very, very well. And it was pretty quick on a desktop machine. It just took about 5 hours of training on 100,000 images. And then when we tested it on 17,600 images, again, it showed very good accuracy. So these are the two plots as a function of the noise in the image. And you can see that for the, if there is very low noise, it was 100% accurate. But when we ramp up the noise, still we get very, very high fidelity or accuracy for the feature averaging case. However, for this edge detection case, the fidelity drops rather quickly. But still, I mean, in experiment, I should notice that in experimental images, typical the noise level is about 2 to 2.5%. So we still expect above 80% fidelity in those situations. In here, we just theoretically, just to check the change in the fidelity, we have ramped up the noise to a very high level. So overall, the message is that the convolutional neural network trained on these sort of STM images with realistic noise levels is very successful. It can tell you the exact location of the phosphorus atoms and also the number of phosphorus atoms in a cluster based on just the measured STM current. So future considerations, we haven't done any optimization of the convolutional neural network in our work. We rather focused on making the STM images simplified by edge detection or by feature extraction. But in future, in principle, you can leave the image as it is, but you can do more optimization of the convolutional neural network by having many max pooling steps and simplifying images in that way. So that's another area which we can focus on and compare the efficiency. We can also look at other machine learning classifier techniques, for example, SVMs or random forest classification, and see how it compares with convolutional neural network. We also plan to do direct testing on experimental images, which we haven't done, although we have included the noise levels which are commensurate with the measurements. We can also look at other larger clusters of donor qubits, or we can also go beyond the donor qubits, and we can use it for STM, in situ STM calibration. So this is all about my talk, and I just wanted to acknowledge my group. Thank you very much for listening.
Thank you very much for the interesting talk, Mohammed. Okay, let's go to questions. I already see something in Q&A. Which is the proportion of the real data to simulations in your training set? From Natalia Ares.
Sorry, what? Can you repeat?
What is the proportion of real data and simulations in your training set? Did you use both, only simulated and some real, or how did you create the training?
Yes, as I mentioned, that this study which we published as our first study, that is based on simulated data only. So there is no experimental data involved. This is something which we want to do in future. But we have included, I mean, there are a couple of things you should notice. First of all, as you can see that the comparison between experiments, so this is real data. So the experiment is the real data measured by STM tool, and this is our computed data, which is from the simulation. And you can already see that the agreement is extremely well. So we had more than 80%, even based on like thousands of pixel by pixel comparison, we had 80% or above match between experiment and theory. So it is already a very good agreement. And on top of that, we looked at the typical blurring or asymmetry noise, which is present in experiment and included in the simulated data. So although our study is based on simulated data, but we expect to work, that it will work well when tested against experiment.
Great answer, thank you. I was wondering, so you do supervised learning with this convolutional network, right?
Yes.
Can you say a little bit, so there were two specific cases. Can you say a little bit on the structure on your labels? Like how do you label the data and which is the categories that you distinguish actually?
Right, yeah, so I think in interest of time, I passed that very quickly, I realized. So as I said that in order to do this classification, so we have developed a scheme to systematically label those atomic positions. So we have a silicon crystal. We know where the atoms are in the silicon crystal, where we can, what are the allowed positions to put phosphorus atoms. So in this study, we used only clusters of 2 phosphorus atoms or isolated phosphorus atoms. So this is one typical example. So if there is only one phosphorus atom, we put it at a certain location here and we label it as 0. But then there are, we can put the second phosphorus atom as a nearest neighbor. And we say that if there is one more phosphorus atom, it is a class 1, then class 2, 3, 4, 5, so on. So that's how we label these atoms in the phosphorus atoms in this structure. And then based on those each location number, we calculate the image, that as if there are phosphorus atoms, and what will be the STM image measured. And then that is the basis for our classification scheme, because when we do the supervised learning, we divide all those images in those classes based on these numbers. And then we say that now there are many images in each class, and now the convolutional neural network can learn and identify and associate images with those classes. And then an unknown image comes, the convolutional neural network will be able to tell us, okay, this image belongs to 13 class with highest probability, or it belongs to 21 class with highest probability. And that allows us to map it back to the atom positions that we have placed the phosphorus atoms on.
So you have
answer the question?
Yeah. So you have actually very large amount of classes, and you still get such a high fidelity. That's very impressive. Let me now ask Justina to just unmute herself and ask her question in person. She wants to ask something. Please go ahead.
Hi, it was a really good talk. I was wondering if you guys are planning to share the data that you generated with the community.
Which data? So the STM data?
Yeah, like the simulated data with labels or the real data.
Yeah, sure. I mean, yeah, of course. We are happy to share the data. I mean, these are lots of STM images. So if somebody is interested to look at them, I can place them in a repository. That's should not be an issue.
Thank you.
Yeah, no worries.
Okay, I think we are just at the time mark, so let's close it here. Thank you, Muhammad, for a great talk. Again, I posted the Slack link into your chat. And let me just close this session by thanking a lot by our great speakers. I learned so much. This was really great. If I understand your program correctly, this was your last session for today, and you will be continuing tomorrow around midday UK time. Thank you again to all the speakers, and thank you everyone for listening, and see you tomorrow. Bye.
Thank you very much. Bye.